In this lesson, we're going to talk about Newton's method, which is a numerical algorithm to estimate the root or the x-intercept of a function. You can also use it to try to solve for a value of a variable that makes an equation true. Let me mention from the start that Newton's method won't always work. We will see ways for this algorithm to fail. Additionally, it's not always a practical way to try to solve for something with pencil and paper, so I will use MATLAB as an assistant today. Conceptually, though, Newton's method is a really neat way to use the idea of the tangent line that we first meet in calculus. Let's start with this degree 4 polynomial y equals x to the fourth plus 3x cubed minus 1. This polynomial could have 0, 1, 2, 3, or 4 roots, so let's put up a picture and notice it actually has 2. Newton's method won't tell us that, not without also bringing in other techniques. Let's consider just this rightmost root. Could we try to solve for this by hand? And the answer is no. There is no factoring technique that you can use here to try to solve the equation 0 equals x to the fourth plus 3x cubed minus 1. However, there's one thing that we can do by hand that might help us zoom in a little bit and get a ballpark estimate for where these roots might live, and that's use the intermediate value theorem. Whenever you're using the intermediate value theorem to try to find roots, what you're looking for is a pair of x values that cause the y values to have different signs. I'll explain the reasoning behind this in a second. First, let me just quickly plug in two convenient values of x. Notice when x equals 0, y is negative 1. On the other hand, when x is 1, y is 1 plus 1 minus 1, which is 1. The intermediate value theorem for a continuous function tells you that between x equals 0 and x equals 1, y moved from negative to positive values. That tells us that there's a crossing between those two x values. In other words, our function has an x-intercept or a root between x equals 0 and x equals 1. Let me put back up the graph of this function. You'll see that we're identifying this root on the right. Now that we have a better idea for where our function crosses the x-intercept, the first thing you need to apply Newton's method is a jumping off point. So let's pick an x value between 0 and 1 where we will start our computation. Maybe it's worth pointing out here that you don't have to start your computation between 0 and 1, and you don't have to use the intermediate value theorem. The reason why I did this, though, is because Newton's method can fail. You raise your chance of success with Newton's method if you start your computation close to the root. So whereas I could start with x equals 10 if I wanted to, my chances of succeeding with this method are going to be better if we pick something like our first value for x, which we will denote as x sub 0, is 1/2. Newton's method then asks for us to make a sequence of tangent lines. Let me illustrate this numerically in MATLAB first, then we'll go through it algebraically. So here's my initial seed of 1/2. Let's go ahead and plug that point into the function. That places us on the graph of this polynomial. What Newton realized he could do is then compute the line tangent to the graph of this polynomial through that point just using classic differentiation methods. Now look at its x-intercept. Its x-intercept is actually closer to the root than where we started. That might mean that this is a better point to work off of. So let's take this new point, plug it into the function. Now at this point on the graph of our polynomial, we can construct the tangent line. And now look at its x-intercept. It's a little bit better. So let's start the process over with this new x-intercept. We started with x sub 0, then we made x sub 1, so now we're at the point x sub 2. Let me have MATLAB run through the process all the way up through x sub 10. You'll notice that you can't really distinguish the points because they're converging on the root. In this particular instance, Newton's method was successful and it approximates our root. So a good decimal approximation for this root between 0 and 1 is about 0.64951. Here's what it looks like when we start with an initial guess of 0.25. You'll notice that something different happened. The first x-intercept that we computed with the tangent line was actually farther away. Now, that could be problematic. That could be a sign that the method is failing, but actually, for this particular case, it still worked. Even though our first tangent line actually sent us very far away from the root, relatively speaking, we still ended up converging to the value 0.64951. Now that we've seen those numerical simulations, let's go through the algebra. So consider a differentiable function like the one that we were just looking at. Say you've written it in the form y equals f of x, and you've identified a good jumping off point. Maybe you just have a good instinct for where the root is, or you've used the intermediate value theorem, or maybe somebody told you where to start your computation. Let's go through the algebra piece by piece, and then we will write down a formula that summarizes everything that we've done. So following the diagrams that we were looking at, the first step is to compute the tangent line through the seed when plugged into the function. So through the point x naught, f of x naught. Well, the slope of the tangent line we know is f prime at x naught. So there we're using an extremely famous result from single variable calculus. To write down the equation of the tangent line, we need not only the slope, but also a point which lives on the line. That's going to be this point x naught, f of x naught. So now the point slope form for our line is y equals the known y value, so that's f of x naught, plus the slope, that's f prime at x naught, times x minus the known x value. So that's the point slope form for the tangent line. Finding the x-intercept means plug in y equals 0 and solve for x. We're going to call that x value x1. So let's plug in x1 comma 0. So for the y value, we plug in 0. F of x naught is just a fixed number for our line, as is the known slope f prime at x naught. For x, we're plugging in the new point x1 and then subtracting off of that the original known x point. We need to isolate this x1. Let's see, I could subtract f of x naught over, leaving me with f prime at x naught times x1 minus x naught on the right-hand side. And let's divide by the slope. That gives us our first realization, if we didn't know already, that Newton's method could fail because that slope could be 0. So if we're going to do this algorithm, we need to make sure that we're not ever dividing by 0. All right, then we're trying to isolate x1, so let's add x naught to both sides. I've written this almost exactly the reverse of how I would like to see it, so let me rewrite this formula as x1 equals x naught minus f of x naught divided by f prime at x naught. Now we've done that initial work. We plugged in our seed, we found our first tangent line, and we found the x-intercept for that first tangent line. That's giving us a new point that we want to plug back into our function to compute a new tangent line, to compute a new x-intercept. But now we realize, hey, look, we can just recycle everything we did. So instead of x naught, f of x naught, let's do x1, f of x1. That means I'm just going to update these subscripts. The slope is f prime at x1. The point on the tangent line that we know must exist is x1, f of x1. Point slope form for our line is also just going to involve updating these subscripts. So y equals f of x1 plus f prime at x1 times x minus x1. To get our next crossing, we're going to call that crossing x2, update this formula, and we know that we'll find x2 when 0 equals f of x1 plus f prime at x1 times x2 minus x1. Doing all the same algebra steps before gives us x2 in terms of x1. So at this stage, we realize that we don't need to compute these tangent lines one at a time. Actually, all we really need is that formula at the bottom. So if I kept doing this, attempting to converge on a root for my function, then if I'm at any point x in f of xn, say I've iterated this process n times, then I can iterate it once more. My next point will look like x sub n plus 1, and we will find it by taking xn and subtracting off of it f of xn divided by f prime at xn. And maybe I'll mention one more time here that that denominator cannot be 0. If you're ever working through this computation and you find that the derivative is 0, it means you have to stop your process and pick a different point. So here's a summary of what we've said so far, plus one new remark. Newton's method means to create a recursively defined sequence of points. You have to start with some seed, hopefully well chosen, and from that starting value x0, you generate x1, x2, x3 until you think that this is converging to the root. So when it works, it's a really neat process. But here are two ways for the method to fail. One we've already identified. It's possible for that denominator to be 0, in which case your computation can't proceed. Returning back to the function that we started with, f of x equals x to the fourth plus 3x cubed minus 1. If I tried to start with a seed of 0, I would have a horizontal tangent line, and that would mean that I just couldn't proceed. So in this hypothetical situation, I started with a bad seed, but I also could have gotten there somehow. So maybe I started with a pretty decent choice and I landed on 0. The other scenario I put up here is that sometimes the sequence simply doesn't converge. So let me give you two demonstrations with the arctan function. The first one will converge at the origin, and the second one with a starting seed of 1.4 does not converge. You'll notice we just start spiraling out forever, and if you imagine that it continues, we're never going to converge at the origin. Let's finish with these two problems, and I would love it if you took a moment to pause this video and see if you could work these out yourself. Both of them are phrased a little bit differently than the example that we started with. So first, why don't you take a moment to see if you can recast both of these problems as finding the roots of a function or finding the x-intercepts of a function. So go ahead, pause, and then I will reveal the way to phrase these questions so that it actually does look like our starting example. For this first problem, we are asked to use Newton's method to estimate the square root of 10. In other words, we want x equal to the square root of 10. We're going to estimate that, which means x squared is 10, which means we want to find the roots of f of x equals x squared minus 10. We're just going to estimate this. So what if I found what I believe is a really good seed and then did 2 iterations of Newton's method? We'll cheat a little bit at that point and just go ahead and compute the square root of 10 to see how well we did. So we're going to actually have that value at hand, but what we'll see is just 2 iterations of Newton's method gives you a very good decimal approximation. Now that we have the function we want to work with, we can write down what its derivative is. The derivative, of course, is 2x. That's pretty nice. Let's write down that general expression. Sometimes you can simplify it. So we know that in general, we're looking at Newton's method with x sub n plus 1 equals x sub n minus plug x n into the function, and we get x sub n squared minus 10 divided by plugging it into the derivative, which looks like 2 times x sub n. I'm actually going to break that fraction apart. We'll have xn minus xn squared over 2xn simplifies to xn over 2, and then minus negative, so plus 10 over 2xn is 5 over xn. If you're doing this with pencil and paper, this might be a better form because what we end up with after combining those first two expressions is overall xn over 2 plus 5 over xn. Now let's figure out where we want to start our computation. We want to estimate the square root of 10, which is fairly close to the square root of 9, which is 3. So x naught squared is 9 means x naught is 3. That will be where we start our computation. So x sub 1 will be 3 halves plus 5 thirds. Common denominator here is 6. So we'll have 9 plus 10 in the numerator. That's going to give us 19/6. Okay, let's just write down one more step. x2, which is actually where we're going to stop, is 19/6 divided by 2, that's 19/12, plus 5 divided by 19/6 is 5 times 6 divided by 19, so that's 30 over 19. All right, these numbers are already getting a bit unwieldy. If you add those together, it's 721 over 228, so we're saying that's our approximation of the square root of 10. As a decimal, which is going to be more satisfying, it's about 3.16228 ... Actually, let me put one more digit there, so 0. All right, so it's about 3.16228, etc., etc. Whereas the square root of 10 with the first 6 decimals is 3.162277. So you can see we did a pretty good job with just 2 steps with Newton's method. Okay, again, the second one is also not phrased as finding the root of a function. See if you can write down a function whose root is equivalent to this equality. What we want to realize is that 1/2 equals e to the x times 1 minus x is equivalent to 1/2 minus e to the x times 1 minus x equals 0. So if 1/2 minus e to the x times 1 minus x was our function, we would be looking for a root of the function. So let's use f of x equals 1/2 minus e to the x times 1 minus x. You could also have subtracted the left side over. That would be fine as well. Let's do a few more things by hand. Now that we have f of x, let's do f prime of x. The derivative of 1/2 is 0, and the derivative for the rest of it is going to be the product rule. Differentiate the first, and we have negative e to the x times 1 minus x, and then differentiate the second, and you get just -1. So that overall, if I factor out the e to the x, I'm left with, distribute that -1, and we get -1 plus x plus 1. Overall, it's x e to the x. Okay, so we have the function, we have the derivative. The last thing we need before we begin the method is where we want to start our computation. Take a moment, if you haven't already done so, to see if you can use the intermediate value theorem with some very convenient values for x. So here, if you pick some basic numbers, you'll be able to deduce that there's a root between them. I have to admit that there's no right answer for how to choose the root here, but what I was looking for, if you followed the hints I was trying to give, is that f of 0 is 1/2 minus e to the 0, which is 1, times 1. So overall, it's -1/2. That's less than 0, whereas f of 1 is just 1/2 minus 0, which is greater than 0. So somewhere between 0 and 1 on the x-axis, this continuous function is going to have an x-intercept. At this point, I'm going to stop this computation by hand. The thing is, in order to execute Newton's method here, you're going to have to plug into the exponential function. So in this particular example, Newton's method kind of requires you to do this with a calculator. Now, in order for that to still seem like it's a reasonable algorithm to employ, you want to think, okay, maybe I'm doing Newton's method with a basic calculator that I can plug into, but which cannot solve an equation for me. What I'm going to do now is end this lesson with a video showing convergence to this particular x-intercept. So I'll put up a few different iterations of Newton's method in MATLAB with different starting seeds.